Morning. We had our test yesterday, so we started a new unit today. I have not graded the tests yet just because there's a few people that were still working at the end of the hour, and I wanted to make sure nobody felt rushed, so I just kind of set them aside and decided we'll let them sit there. If anybody wants some more time to finish up or wants to look it over before I grade it, let me know, and I'll give it back to you when we hit homework time today, just so you have some more time to look at it. I don't want anybody to ever feel pressured or rushed on any of their tests. I want it to be a true assessment of what you actually know and can do, and not what you can do under pressure right now. So this unit 2, we're going to start out talking about measurement. Now measurement is kind of an interesting concept because it evolved over time. It's not something that was really well planned out or whatever. Historically, measurement came from a need to communicate. We'll talk about this more in a few days when we actually talk about the units themselves. But for right now, I'm just going to talk about kind of the origins of it. You know, if we were building something or trying to do it the same way, we needed some way to communicate between us that we were doing it the same. You know, if we were in the same room or even in the same building, we'd just go over to each other and hold the two things up next to each other and, oh yeah, they're the same size. But if you're not there where you can do that, we need some way that I could send a message across town or wherever it was, or record it so a year later you could build it the same, or I could even replicate it the same without having it in front of me again. So they used all sorts of things to do that measurement. And again, we'll discuss what those units were and where they came from in a couple more days. But for right now, we'll just assume that they chose something to be their unit of measure. So let's say that this length right here is our unit of measure. Well, they would measure things. Let's say I have, oops, let's make that not so ugly. Let's say I had this object right here that I needed to measure. Well, to do that, I would take my measuring device here, and I'm going to actually trace it here so I have an extra one. And we would take it and we'd say, okay, I'm going to hold it right there. That's 1. I would take it and move it to the end. 2, 3, 4. Well, it's more than 4 and less than 5. You might take a guess, well, that's about another half. You might guess that it's like 4.5 or whatever. That's about as close as we could get with measuring like that. Now, I had the advantage here, excuse me, because when I move it on the computer screen, it leaves the shadow of where it came from before, so I can match that end up pretty exact, can't I? But you can imagine without that, if you're doing this in real life, you're just kind of looking at where the end was, or maybe putting your finger there or whatever, and then sliding it over. So every time you move this thing to the next slot, there's going to be a chance for some error because you're not going to put that beginning end right where it ended last time, right? So it's very sloppy measurement. If you were lucky, you would have 2 of them, and you could put them end to end and flip-flop them like this and kind of do the leapfrog thing with them, and that was a little more accurate. But even then, there was some slop, you know, some dust or whatever on the ends, or when you go to move one, the other one slides a little bit. It wasn't perfect. So to make things better, what they did, they took a stick or whatever they had for a piece of material. Oops, I didn't want to do that. Come on. And they took one of these and they'd set it on there and they'd mark it. Okay, there's 1. 2. And so what this did is it allowed them, rather than having to move them, even if you had 2 having to leapfrog them even, rather than having to move them to measure the object, they could just hold the object up next to it and look at, in fact, they didn't even have the numbers at first. They just had the lines and have to hold it up there and count the number of lines, and eventually decided, hey, if we numbered these, it would go a lot faster. And of course, this was the beginnings of our first rulers. So like that. But now you'll notice here, I'll move these out of the way for now. I go to measure this green object here, and it's still, I'm going to shrink it. Yeah, come on. There we go. You know, it's looking like it's like 4.5 or whatever. I'm going to change this thing just a touch. That's not quite exactly 4.5. So if I were measuring this out, you know, it looks like, you know, 4, a little bit less than 4.5. It's between 4 and 5 is really as precise as we can go with this current measuring device. When you get into measurement theory and stuff like that, they tell you don't estimate in between. It's whatever marking it is closest to, that's what you have to measure it. Because your measuring device is not capable of being more precise than that. This measuring device is only precise to the nearest unit, so we'd round to the nearest unit. It is 4. If I had this piece here, obviously not the same length, is it? But if I were measuring it with this ruler, it would measure as 4. So that this measuring device is not precise enough to distinguish between those two objects. That is the definition of precision. Precision is the ability to distinguish between two objects that are similar in size. This is measuring length, so two objects that are similar in length. This ruler is not precise enough to do that. So how did they make the ruler more precise? Well, they go through and cut each unit in half. Now, if you're looking at this, both of these are still closer to the 4.5, aren't they? So both of these, if I had to measure them with this ruler, would be measured as 4.5 units. So it's still not precise enough to distinguish between them. So what they do, they came and cut each of those units in half. Now, the green one is closer to 4.5, and the blue one is closer to 4 1/4. Now this measuring device is finally precise enough to distinguish between the green and the blue objects, whatever they are. One question always pops up. Why did they divide them into halves, fourths, and eighths instead of doing something easy like tenths? Well, you got to think of what they had for technology. Dividing something into tenths is relatively difficult. If I wanted something to be half as long as this sheet of paper, what would I do? Exactly. Fold it. Now I've got exactly half of that. And that's exactly what they did for these measuring units. They found something flexible, cut it that length, folded it in half, and they had half a unit. So that's, and then of course you'd fold that in half, and now you have quarters, and you fold that in half, and now you have eighths. So that's exactly why it ended up being halves, quarters, eighths, sixteenths. Because your powers of 2 as you fold things in half. Now we'll notice here, I said the green one is closest to the 4.5 mark right now. But it's not exactly 4.5, is it? On this measuring device, anything between here and here would actually be measured as 4.5 units. How far away from 4.5 could this really be? How far away would that be? Well, it's halfway to this next division, right? So how far is it from here to here? A 1/4 inch, right? Or a 1/4 unit. So that means the red up here could be half that or 1/8 of a unit. So what we're going to use those to define a couple things about our measuring device. Something called the degree of precision. Again, the degree of precision is also describing its ability to distinguish between similar objects. The degree of precision is the smallest division. So on this measuring device, that degree of precision is the 1/4 unit. And then there's the possible measurement error. We set up here, anything that's from here to here is going to be called 4.5 units. That's the possible measurement error, which is half of the smallest division. Half of the degree of precision. So for this device, that's the 1/8 unit. So that's one of the first things we have to look at, is looking at a measuring device and defining degree of precision and that possible error.
What is that, half of what?
Half of DOP, degree of precision. All right, I'm just going to go up to 2 inches here. So the first thing we want to find here is the degree of precision. The degree of precision, again, remember, is the smallest division. Now, to figure out what that is, generally I look at 2 whole unit marks. We're going to assume this is in inches just because I'm tired of saying units, so I'm going to put a unit on it. This is inches here. I generally do not go from 0 to 1. Can you tell me why? The end of the ruler is not very precise. Either a lot of times, if it's just a regular ruler, over time they get rounded off a little bit or worn down. On tape measures, you've got the hook on the end, and that actually slides in and out. It's meant to slide in and out for external and internal measurements, so it adjusts for that. But it also covers up some of those markings so you can't see the very beginning of them much. So usually I'll go from 1 inch to 2 inches, or 1 unit to 2 units if it's something other than inches. So from here to here, to figure out what the size of each of those divisions are, we just have to figure out how many divisions are between those whole units. Now, because I generally like to take the easy way out, if there's a clear halfway point, I use that to my advantage. Is there a clear halfway point here? Yeah. That one, we're pretty sure that that's the halfway point. So now instead of having to count all the divisions, I only have to count half of them and double it. Now I'm not counting the lines, I am counting the spaces. So there's 1, 2, 3, 4, 5, 6, 7, 8. So that means there's 16 spaces there. So each space is a 1/16 of an inch. So I have a degree of precision of a 1/16 of an inch. What is my possible error here then? 1/32. Very good. That is found by taking the 1/16 times 1/2. Half of that degree of precision. What that means is if I report a measurement as being 3 1/4 inches. What that really means is that is 3 1/4 inch plus or minus 1/32 of an inch. Because anything that's within a 32nd of the 1/4 inch mark is going to get rounded to 1/4 inch. Here is my 1/4 inch mark right here, right? Well, you can see anything from here to here is going to get called a quarter. It would be 1 1/4 here instead of 3 1/4, but you get the picture, right? So if I report it as 3 1/4 or 1 1/4, it's not exactly a quarter. It's just closest to a quarter, so it could be up to halfway to that next division. So every measurement, when measured by a device like this, has a plus or minus on it, an error on it. It is implied by the precision of that measuring device. Now for you guys, that's probably more important than for most groups because you guys are going to deal with a lot of precision measurement in machining. You're going to be measuring down to the thousandth or 10,000th of an inch regularly. Depending on where you go, there are companies in this area that have been known to measure, for their tooling side of things, to measure down to a millionth of an inch. I know Hutchinson and Eau Claire has a few applications where they measure down to a millionth of an inch. So you're looking at very precise measurements. So that degree of precision is a big deal. Now you might think that 3 1/4 inches is 3 1/4 inches, but it might not be. That's supposed to be a broken stick. So here's one of our measuring devices. That's the section between 3 and 4 inches. Here's another measuring device. On both measuring devices, I measure something. If I report it as 3 1/4 inches on this measuring device, what does it really mean? Well, what's my degree of precision over here? A 16th of an inch again. Between 3 and 4 inches, there's 16 spaces, so each one is a 16th of an inch. What is my possible error? 32nd again. So plus or minus a 32nd of an inch. So what that means is when I report this as 3 1/4 inches, that is 3 1/4 plus or minus 1/32 of an inch. So that gives me a range. 3 1/4 minus a 32nd of an inch. So 1/4 is 8/32. So that would be 3 7/32. I'll let you guys verify the subtraction there on your own if you want to. 2 3 1/4 plus a 32nd of an inch, which would be 3 9/32 inches. That's a fairly respectable range. I mean, it is a 16th of an inch, so in machining that would not necessarily be acceptable depending on what you're doing. But it's a fairly respectable range. Over here, however, if I report something as being 3 1/4 inches measured on this device, what is the degree of precision? Careful. The degree of precision is only 1/4. Possible error is an error. It is an 1/8. You got it. So what that means is that measurement of 3 1/4 is 3 1/4 inches plus or minus an 1/8 of an inch. What does that give us for that possible range? Well, 3 1/4 minus, there you go. Perfect. 3 1/4 minus an 1/8 is 3 1/8. 3 1/4 plus an 1/8 is 3 3/8. That's a pretty wide range. It's a full 1/4 inch. Not even in the wood shop is that going to be acceptable, right? So 3 1/4 inch, you think of 3 1/4 inches as being 3 1/4 inches. It's not. 3 1/4 inches can mean two very different things depending on the precision of our measuring device. And when we work with measurements, we have to keep in mind some knowledge of what the measuring device is capable of. Now in standard measurement, because the quarters, halves, eighths, and whatever, it's a little more difficult because there's nothing implied in the number. You have to know something about the measuring device. You have to be told that that measuring device is capable of a certain amount. So if, let's say we measure 7 3/16 inches on a 1/64 inch ruler. I've seen steel rulers down to a 1/64 of an inch. They're really tough to read because you have to really get close to them and have good light to see them. But I've seen them down to a 1/64 of an inch. So that means the degree of precision is a 1/64 of an inch. So what's the error? Plus or minus 1/28 of an inch. So this is plus or minus 1/128 of an inch. Create the range for me quick. Not an easy common denominator to do, is it?
No.
What do you multiply 16 by to make it 128?
8.
8. So 3 times 8 is 24, right? So that's 24 1/28. One less would be 23. One more would be 25. So 7 and 23 1/28 inches to 7 and 25 1/28 inches is that range. That kind of looks like it says into in there, but inches. For you guys, fortunately, machining has switched over. They don't use the 1/64 inch anymore. You've gone to a metricized measurement. Now, that doesn't necessarily mean you're using metric units. That means you're using a decimal inches. You're using down to the thousandth or the 10,000. So when you go away from this fractional thing and down to that decimal units, this whole thing is much simpler to deal with. This is a question I always get a very surprising answer to. Is there a difference between those two measurements, 3.2 inches and 3.20 inches? Well, numerically, no. They're the same number, same numerical value. Measurement-wise, though, there's a very big difference between them. And this is where a lot of people get confused because there is a difference between numbers and measurements. Measurements have their own little set of rules that they deal with. And even though numerically, by the numbers, these two are equivalent, if you go into the rules of measurement, which add extra rules onto things, they're not. This one here is implying that the 3.2 is implying that we measured with this device and it's closest to the 3.2. So that means it could be anywhere from here to here, and it comes closest to 3.2 inches. Makes sense, right? This one is implying that we measured I'm not going to draw them in for the whole thing, but we measured with a device that's at that precision, and our object was somewhere in that range. That's a very big difference, isn't it? So the extra 0 on the end doesn't change anything numerically, but it changes our possible error in our measurement. It's telling us that those extra decimal places are telling us something about our degree of precision. So our degree of precision is the place value, not of just the last digit, but we're going to call it of the last. You're going to cringe when you hear this word. Significant digit. Here's where I said the rules of measurement differ from the rules of numbers and get a little confusing. In measurement, the word significant means something different than what you're used to too. I mean, we're used to significant meaning important or meaningful. Here, significant means it is part of the measurement. It is significant to the measurement. Okay? So here, 3.2, that has a degree of precision of 1/10 of an inch. 3.20 has a degree of precision of 1/100 of an inch. We're going to talk a little bit more about what a significant digit is in a minute. But for now, it's that last digit in each of these. So then, of course, our possible error is still just a half of that degree of precision. So the possible error here is plus or minus what? 0.05 inches, half of 1/10 of an inch. This is plus or minus what? 0.005 inches. So in other words, this one is implying a range of 3.15 inches to 3.25 inches. Where this one's implying a range of 3.195 inches to 3.205 inches. Make sense? Okay. So we got to talk a little bit now about what significant digits means. Significant digits means it is necessary to define the measurement. Significant digits are all non-zero digits.
Can you go up one more time?
Yep.
Red.
So all non-zero digits are significant. So that's the easy part. If it's not a zero, it's significant. The tricky part are zeros. Zeros if they are not otherwise needed for the number. The one exception to that is if they're between other significant digits. So what do I mean? Well, if I have a number like 804, obviously the 8 and the 4 are significant, right? Because they're not zeros. The 0 there is between two other significant digits, so it must also be significant. So zeros in the middle of a number are not a problem. They're between other significant digits. They have to be significant. There's no question there. So the question becomes, are these two zeros significant? No. Why not? They are needed for the number, not otherwise needed for the number. They are needed for the number here. And this is where that whole significant comes in. These two zeros are very, very important. If I take them off, it's a 92, not a 9,200. So I can't take them off. They are needed to define the numerical value of those other digits. So that means we're just assuming that they're numerically and not part of the measurement. Well, what if they were part of the measurement? They would have to be indicated. What does that mean? Well, that means there's a difference between 9,200 inches, or millimeters, or whatever, and 9,200. That little line below, or sometimes above the 0, is indicating that it's significant. What this is saying is our measuring device was only capable of going to the hundreds of an inch. We happen to be closest to 9,200. So this is a degree of precision of 100 inches. So it's a plus or minus 50 inches. Does that make sense? Yeah. Unless otherwise indicated, we have to assume that those zeros are only there to define the number, that they're not part of the measurement. We have to assume that this measurement is rounded off to the nearest 100, the last non-zero digit. Here, since that 0 is indicated, we now know that degree of precision was 10 inches. It was measured or rounded to the nearest 10 inches. And so it has an error of plus or minus 5 inches in it. So for this one, is this 0 significant? If I took it off, would it change the meaning of the other numbers? No. So the only reason for it to be there. Now, like I said, this is where it gets confusing. Because we want to think significant means important. These zeros were important to that number, but they were not significant. This 0 here is not important for the number, is it? I can take it away. It doesn't change the meaning of anything else. But it is significant. Because there's no reason for that 0 to be there unless it's part of the measurement. Does that make any sense? I could take that 0 off and it wouldn't change anything. So numerically, it's not necessary. So the only reason for it to be there is because it's part of the measurement. So this has a degree of precision of 0.01 inches. So it has an error of plus or minus 0.005 inches. What do you think? Okay. So then how about this one? Looking through this, is this 0 significant? Yeah, it's between the 3 and the 9 are significant because they're non-zero and it's between them, so it has to be. How about the zeros at the end here? Well, this one wouldn't be on its own. If the number ended there, that one wouldn't be. But these zeros back here, is there any reason for them to be there? No, if I took them off, it doesn't change the meaning of the rest of the number. So they have to be there, or they don't have to be there, which means they must be part of the measurement. So those are significant because the only reason to put them there is if they're part of the measurement. So once they're significant, this one is. This here has 6 significant digits. Those zeros are going to be confusing. It'll take a while to get used to it. So we've defined the degree of precision of a number. Let's define something called the accuracy. The accuracy of a number is nothing more than the number of significant digits. So this number up here had an accuracy of 6 significant digits. So let's look at some numbers and see if we can define their accuracy or their number of significant digits. How many significant digits? 2, good. How many significant digits? 5. All 5 of those are significant. This is an example we haven't done yet. We know those 3 are significant, right? What about these zeros up here? If I took them out, would they change the meaning of the other digits? Yes, so they are necessary for the number. Since they're necessary for the number, that means they're not necessarily part of the measurement. So no, they are not significant. This only has 3 significant digits. Again, that's the confusing part of it. is we think significant and important are the same thing. They're not. Those zeros there are very important. If we take them out, it changes the meaning of everything. But they're not significant. They're not part of the measurement. They're only there to define the value of these digits. Which it gets kind of weird, doesn't it? How many significant digits? All 5. The 0 at the end, if it's after the decimal point, if it's after other significant digits, it'll always be significant. These, they're after the decimal point, and they're not preceded by any, they're not after any other significant digits. So those would not be. So if they're after the decimal point, it's a little bit easier to reason with. After the decimal point, they're only significant if there's a significant digit before it somewhere. Okay, how about how many significant digits? 2 significant digits. How about this one? 4. Very good. Once this one's indicated, it has to be significant. That makes this one significant too, because it's between that digit and other significant digits. What's that? Just 2? Because the zeros at the end here have to be there to provide value to these, so they're not necessarily part of the measurement. We cannot assume they're part of the measurement unless we're told to. When we look at this, when you're dealing with measurement and precision measurement, you always take what's called a safe assumption. You assume the worst case scenario. And that worst case scenario would be that this measurement was rounded to the nearest 1,000. There really was other stuff here, but it was just rounded to the nearest 1,000. So that it's not precise beyond that digit. So that means these zeros aren't part of the measurement. They're just rounded off and filling the places. The only way you can assume those digits are significant is if it's indicated like it was here with this line underneath it. That's telling us that we didn't round to the nearest 1,000, we rounded to the nearest 10. So this last 0 is not part of the measurement, but these 2 really are. We just happen to come close to the 38,000. Yeah.
Well, it's 0.2999999999.
Okay, so you're talking about continuing. Like this?
Yeah.
Okay. Here's the thing. Would you ever take a measuring device and hold it up there and get 0.299999? No. This, as it repeats, would be part of a calculation. Here. There is, all these up here are measurements. So the significant digits have to be implied within the notation of the measurement. Now, after those measurements are taken, if you use them in calculations, which we'll start talking about tomorrow, as you use those measurements in calculations, you have to do appropriate things with the significant digits. Now, for us in here, we're going to use them over the next few days, and then after that, we're going to loosen up. I'm not going to make you do all your calculations to proper significant digits.
So if you got like 5.0230,
yeah,
you add it or whatever to that number, you're going to have 5 significant digits. You're going to go over.
Yeah. Whatever, so this is going to be calculated. Whatever numbers we used to calculate that, there's going to be two inputs. We'll just call them A and B. We would use the significant digits from those two. And those two, I'm assuming, would be measurements of some sort.
Right.
We're using the significant digits from those measurements to determine what significant digit this has to be rounded to. When you do calculations with these measurements, you do have to round to proper significant digits in your answer. And like I said, we'll talk about that more over the next couple of days. I'm not going to be really strict on that in this class. We're going to do it here in this unit so you see it and know what it's like, so that for you guys, you wouldn't necessarily be doing that yourself. It'd be a mechanical designer or an engineer somewhere that's doing the drawings or whatever that would be making those rounding for you. But I want you to see it so you can look at what the calculations that somebody else did and understand why did they multiply this times this and get this when there should be like 4 more digits on the end of that, because they're rounding to significant digits for the measurement. For right now, we're going to have you guys in your big book. On page 225. Exercise 7-6. I believe it's 1 through 20, the odd. 1 through 19, the odd, basically, then. 225, I believe. Exercise 7-6. Now, if this is a bit foggy to you right now, hang in there. I mean, this is a new way of thinking for a lot of you. Unless you've had like a high school chemistry or physics, you've probably never heard of significant digits, or you heard the word and never knew what it was about. Right now, for this assignment, mostly what we're going to be looking at is that degree of precision and that possible error. There'll be a little bit about significant digits, because remember, degree of precision comes from that last significant digit. And they are going to ask about accuracy a little bit, and they might ask about the accuracy. Maybe that's the next assignment, but which is just your number of significant digits. So for right now, that's all I'm terribly concerned about, is that you can find the degree of precision from the decimal place value, and that you can find the possible error that's built into that measurement, and maybe start to try to count the significant digits. But we will go over significant digits more in the next couple of classes. We're going to start talking about calculations with them. It's not something we're going to harp on for the whole semester. If this were tech math for mechanical design, from this point on out for the whole rest of the semester, I'd make you do all your calculations to the proper significant digits. For you guys, it's more of a let's get acquainted with it so we understand it when we're looking at somebody else's work type of deals. Okay, well, I'll give you guys the last 8 minutes to get started on that.